This video has been supported by Skillshare. After mastering mobile oscilloscopes and motorized screwdrivers, the TS100 company Miniware is expanding into even more territories. Quantity and detailed description of contents says tweezer, so there you go. Somehow I had expected soldering tweezers or multimeter tweezers, not tweezers. And what on earth is an M-scraper supposed to be? Well, a bar of Damascus steel with one ground chisel tip apparently, for your everyday scraping needs. It's nice, sharp, comes with a genuine leather sheath, and a sharpening stone which is a bit too coarse for my taste. I prefer an 8000 grit Arkansas whetstone for CNC deburring as well. I've had this thing for a few months now and it's certainly an optional specialty tool. But on average I've touched it more often than the electronic screwdriver actually. Mostly for post-processing 3D prints. And unlocking riveted tweezers. These are also nice, but they don't fit into my established tweezer strategy. I like to keep a stock of these very cheap tweezers around and treat them like consumables. And then I've got a pair of exquisite Sunday tweezers. Made in Switzerland by Weller Erem. $50 for this one though. The square-jawed Miniware pair is going to withstand improper handling a lot longer than the cheap ones do. The other one is visually attractive, but it doesn't really blow me away. This thing kind of does. It's a laser distance sensor from Micro Epsilon. This particular model has a 10mm measurement range only, but an incredible 100 nanometer resolution and a 500 nanometer repeatability. To finish a disassembly job 5 minutes earlier, somebody has snipped off the cable, which is a bit of a shame, but it gives us the opportunity to check out what's inside. Given its incredible specs and price tag, I would have expected this thing to be based on laser interferometry. But it's actually just a long image sensor onto which the reflection of the laser point is projected. That happens to be a very similar method to the one that's used in these Chinese LiDAR scanners. But I assume that for the sub-micrometer performance it needs to do error mapping. Maybe even thermal expansion compensation in software. It wants to talk RS422, so I've attached an HDMI cable that has both shielding and twisted pairs for signal integrity. I've also printed a new cable gland that bites down gently on the isolation when that red corner is back in place. Yeah, I admit it, I care about this thing. Look how it adjusts the laser brightness automatically to match the surface it tries to see. So cute. One can use it to measure how not parallel these parallels are. Or to check the thickness of a solder mask layer. Interestingly, it has an analog output as well, and it can be configured for a 4 kHz sample rate. How about recording some infrasound with that? That's not infra enough. How about a laser tone wheel based Hammond organ? No thank you. Aren't there any infrasound sources around? I need an elephant or a rocket launch or something. Dexter, go find. Nah, that yapping is not infra enough either. Ah, I see. Well, that is almost a rocket, but I'm not sure if it's going to work. Ideally, I would have to take a measurement all the way up there, and from a perfectly immobile reference tower. But the budget for this production didn't quite cover that. Maybe next time, if we sell enough tweezers. So luckily, the thing decided to change gears and head direction while we were there. And it made that weird noise, almost as if in response to our intrusion. I'm not sure if any of that will make it into my laser audio recording, but let's grab the data and get the hell out of here. I'm using Miniware's new MDP power supply to generate a precisely regulated 12 volt from a USB-C power bank. And I wanted to use their DS213 oscilloscope to record the waveform. But that signal was way too small to be visible. So I used my smartphone with a USB sound card, which happens to have a microphone preamp built in. I wish it hadn't, because that way I revealed the voice of the ancient evil whose disguise this wind turbine is. No wonder Dexter was eager to leave. Wanna hear it? No thanks. Here are a few more details about that Miniware power supply. The only set that's available at the time I'm making this video consists of a control module with a flip-out color LCD and one power supply module. The portable modular design is kind of the #1 feature of this product. They are planning to release a lot more of these modules in the future, like an electronic load or a battery charger. And then those can be stacked and controlled with a user interface slice on top. Or anywhere else. The modules are communicating wirelessly, and I think everybody who's working with isolation or vacuums a lot will love that feature. I'm not yet, but I kind of do in anticipation. Here's my cooking pot vacuum chamber. I've printed this siren almost a year ago, knowing for sure that one day an opportunity would present itself to put that in a video for some absurd reason. And what do you know? Here it is, the world's first low-noise vacuum air raid siren. To be superseded soon by something a little bit better. Here's what the manufacturer has to say about that MDP power supply. By the way, nice product photo. Does that small brushless gearbox motor look familiar to anybody? So the MDP-XP is marketed as a linear DC power supply. Mentioning linear and high efficiency in the same sentence doesn't really add up though. 0.25 millivolt ripple is quite a bold claim. That would be better than my full-size linear bench power supply, which costs twice as much. They say it can put out 30 volt, 5 ampere or 90 watt, whichever comes first I assume. But if it is in fact based on linear regulation, it's going to be much more interesting to see how much power the thing can dissipate internally. Because if you feed it 30 volt and draw 1 volt at 5 ampere, its poor little aluminium body would have to dissipate 145 watt, which it can probably do for like 3 seconds before needing to cool down for half an hour. Support positive and negative pressure? Well, you can flip the leads, I guess, but you can't program negative output voltages. That's going to be an OSMU exclusive. Series pressurization? Not effortlessly. The in and outputs are not isolated, so if you want to connect multiple power modules in series to reach a higher output voltage, then you have to keep their supplies isolated. For example, one big LiPo battery or power bank per slice. Let's see how it tries to fulfill those claims. There seems to be a bug in the firmware that kicks you out of the editing mode. As if editing numbers with 2 rotary encoders wasn't inconvenient enough. I'd like to see dynamic velocity in a future firmware that makes you go faster and faster when scrolling in the same direction for some time. But other than that, the programmed current matches the value that the MDP measures reasonably closely. And the current that's actually coming out, according to Keithley, is always close enough to the set point for all purposes that I would use a small mobile power supply for. In no case did it reach its insane output accuracy spec of 0.025%, but it's usually better than 0.5%, and that is, in my opinion, good enough. Voltage-wise, it has a 10 mV programming resolution, and is similarly good, but not always within spec, output accuracy. It's also in the 0.5% neighborhood. Oh, did I mention what an absolutely terrible way of entering numbers this is? It is, and it needs to go. Here's another idea. Take one of those unused push buttons and display fine above it. Whenever it is pressed while scrolling, the user can adjust millivolt or milliampere. That's not needed all that often, so when not pressed, you just have a default 1 volt or 100 milliampere programming resolution. Hold up. What is going on? It gets 12 volt from a quick charge USB power bank. Where the hell did it find 20 volt all of a sudden? Okay, that's actually illegal. I'm calling the police. No, seriously, it has a boost converter, and it generates up to 30 volt from an ordinary USB power bank. That is really cool. Why didn't anybody tell me? Hell, why didn't they put that more prominently in their spec sheet instead of series pressurization or whatever? Well, boost converter outputs are usually not that clean, especially when you squeeze them into such a cute little pocket-sized enclosure, with no space for large smoothing caps. I wouldn't be surprised if there was a conflict with their specified world-class ripple figure. I wouldn't mind if there was. Turning USB outlets and power banks into adjustable 30-volt lab power supplies is a noble cause that justifies all means, including violation of the USB standard. When necessary, the thing unscrupulously draws almost 4 ampere from 5-volt supplies. With the cheapest unprotected USB chargers, that can cause damage or be a fire hazard. Luckily, it has a TS100 compatible DC barrel jack as well. For ripple measurements, I'm going to feed power from a trustworthy source into there, because my USB power banks are passing out way too quickly. This way we can play around with the highest possible power and look at the effects of various in- and output configurations on noise and transient response time. I was kind of hoping to make their own mini oscilloscope snitch on a family member by showing me some voltage ripple in the 10 mV per division setting. Luckily, for all parties involved, nothing. So we've got to look more closely with this antique of an HP differential probe, its AC coupling head, and the shortest possible antennas. I can't quite catch the entire setup on camera, but luckily Tektronix makes its display available via web browser, which I'm just going to record and put it here somewhere. Here's sort of my background radiation, coming from the environment or the electronic load. I'm positively surprised here, but I have to say it. The output doesn't even have to be enabled for the MDP under test to exceed its 250 microvolt ultra-low ripple spec. Be it RMS or peak-to-peak, this is still a spectacular result for such a compact boost converter. Here I'm feeding in 5 volt to have them doubled to a 10 volt output, from which I'm drawing 1 ampere. That causes no more than 5 mV peak-to-peak noise on the output, before it safely taps out because of input overcurrent. Here I'm regulating down from 5 to 3.3 volt while pulling a lot of current. Noise is even better, but the voltage is too high. Strange. Could this be an attempt at compensating voltage drop over the test leads? If so, I would advise against it. It's a natural effect that everybody expects. If it's overcompensating on the other hand, it's just confusing. Now I hope I can make it sweat at least a little bit by boosting 5V in all the way to 30V out. Well, the internal temperature, according to that number on its display, doesn't really seem to change a whole lot in no scenario so far. But at least we are getting some more noise now, confirming that the thing in fact has to obey those same annoying laws of physics that are making my own power supply design so damn difficult. Still, we are staying well below 8 microvolt peak to peak, and that may well be the closest thing to a supernatural phenomenon I've ever seen. Feeding in 24 volt from something like a TS100 battery pack gave me very similar results. The difference is that there's much more power available before running into that input overcurrent condition. Here I'm boosting 24 to 30 volt and I can draw over 70 watt from the outputs without anything blowing up. It's not even emitting a threatening hiss or that inexplicable smell of overheating semiconductors. Again, about 8 millivolt peak-to-peak noise worst case. In the final scenario, I'm regulating 24V in to 12V out, and to the surprise of nobody, it's doing that really well. For comparison, some high-end multi-$1,000 lab bench power supplies can guarantee you sub-millivolt ripple and noise, but none of them are this cute. None of them will get a range of expansion modules, and especially none of them will be partially open-sourced. I'm now a little bit taken aback by this over-voltage at high current behavior, but otherwise I'm very impressed by this thing's performance. When I saw them mentioning high efficiency in their datasheet, I was totally expecting something like this. This is another popular Chinese switching power supply that sure can put out a lot of power at the cost of being obscenely noisy. Instead, what they've come up with is another uniquely useful mobile bit of kit. It won't replace my full-size benchtop unit on the bench, but everywhere else. On repair missions at friends, while diagnosing CNC problems, and while making laser measurements of haunted wind turbines. One more thing, although I'm fairly sure that there's nothing I can discover that'll change my mind at this point. Here's the current that it puts out in response to a shut-in short circuit. It's not as clean as I would have hoped, and it does put out more than the set current in these short pulses. But at least it's just that, short pulses and not a substantial output capacitance that pours out before the current limiting can take effect. Both of my linear power supplies are guilty of that, and with those it looks like this. Here's the perfectly beautiful response to repeated 3 ampere pulses in the middle of 100 milliampere idle. No complaints whatsoever. Now that's finally all I can think of testing. Wanna know how they did it? Yeah, me too. But before screw diving in, I'd like to document that we've been talking about switching pre-regulators for the OSMU back in April and before. So if that's their trick, I'm not going to steal it. At least not from them. Maybe from National Instruments, who have published an interesting article about that a long time ago. This video is long enough and my voice is wearing out, so I don't think it's worth it to take apart the control unit. There's going to be an STM32 and a wireless transceiver in there. This is where the almost magic is happening. It'll also have an STM32 of course, because that's Miniware's go-to processor, and a favorite in the open source community. It's even in their screwdriver if I remember correctly. And I usually do. Underneath the lid there's a big magnet that holds the stack together loosely, and a few dabs of thermal compound. The heat-sinking vias are covered by solder mask and the lid is covered by anodizing, so no isolation necessary apparently. The banana receptacles are these gold-plated chunks that are just screwed down to the board, making the teardown experience as pleasant as always. Oh wow. Very high complexity on very little space. Pretty much what I expected from the performance that we were seeing. I wonder if they are even ready to publish schematics for this thing, because this has taken some time to develop, I'm sure. Here's the relatively unexciting digital half, with a heat-sinking pad and a temperature sensor for that switch mode inductor. That seems to be their prime suspect in regards to temperature. The other potential hotspots can be found by looking at the placement of the thermal compound. It's the MOSFETs that are driving the inductor, of course, and a few more lonely transistors right next to the output. Let me try and put 2 and 2 together, subtract e to the power of I times pi, and walk you through this powerful circuit superficially. Power comes in through a fuse and gets buffered in a first set of electrolytic caps. That HM4301 chip at a 45-degree angle is a buck boost controller. It uses the power devices in its neighborhood to convert a wide range of input voltages into an intermediate voltage that's just a little bit higher than the currently programmed output voltage. That's what I meant earlier when I said that the output of such a switcher is not that clean. So it's buffered and smoothed slightly in a second bank of electrolytics. And then smoothed even further with a long ferrite bead, a big inductor, and a third bank of electrolytics. The voltage here is still a little bit too high, but now fairly clean. The final regulation to the output voltage is done by these transistors in a linear mode. And the terrible energy efficiency doesn't matter, because it's just such a small drop. Over here is a low-side current shunt and what might be a traditional differential amplifier made from 3 discrete op-amps. By reconnecting that flat flex cable and that miniature pin header with a piece of wire, we can also operate the thing open and verify my theory. Yes indeed, it's configured for a 10-volt output, but that pre-regulator is constantly generating 500 mV more, even with the output disabled. That blue LED seems to be an output OK signal. No idea about that faint red one. On closer inspection, it looks like only the first of those 3 transistors near the output is responsible for that final 500 mV regulation step. The other 2 could be for protection against reverse current flow back into the output. Beautiful, all the way through. Just like the Skillshare class I'd like to show you this time. It focuses on the user experience in mobile app development, but the underlying ideas carry over and apply to everything that has a user interface, like our MDP or other hypothetical power supply design projects in the future. Skillshare, an online learning community for creators, has over 25,000 similarly interesting classes in design, business and more. A premium membership gives you unlimited access so you can join the classes and communities that are just right for you. Whether you want to fuel your curiosity, creativity or even career, Skillshare is the perfect place to keep you learning and thriving. It's also super affordable with an annual subscription costing less than $10 a month. So go ahead and join over 7 million creators who are already learning with Skillshare. Use the link in the video description for a 2 months free trial. And that's all I have for today. Thank you for watching.